I'm Ria.
I'm Caleb.
I'm Ayush.
I'm Kenzie.
And our team is working on an e-textile hacking project under the guidance of Thad Starner. So lately, Georgia has passed a law on hands-free driving, and it's a bit of an inconvenience to us because we are so dependent on our devices. Luckily, e-textiles can actually help since they allow us to interface our devices while our eyes are busy. So e-textiles has been a research topic for a while, except it's not scalable and not very reliable. Until 2014, when Google came up with Project Jacquard. So in Project Jacquard, they essentially developed this conductive yarn that is braided metal and silk so that it can withstand harsh manufacturing techniques as seen in the video, and also look and feel natural and aesthetic. In 2015, Google and Project Jacquard partnered with Levi's to develop the first commercially available e-textile called the Levi's jacket. And though it exists, its functionality is limited, so that's where we come in.
So before I start, I'm just going to pass this around. You guys can mess around with it. So our project for the last couple semesters has been to open the Jacquard and its functionality. As it stands right now, the jacket is actually pretty limited in what it can do. So our goal is through some developer-friendly toolkits, we plan to open up existing functionality as well as additional functionality that we created for developers around the world. So our team is actually split into two sectors. We have hardware and software. Myself and Ayush were on the software side. So just a little example of the most recent addition to our toolkit is the QR code connection. So inside each jacket, there's a QR code connector. From a developer standpoint, it's as easy as one line of code. From a user standpoint, as you can see here, all you have to do is scan the QR code, pop the tag in, and you're connected to that jacket and ready to go.
So, like Caleb said, I am also on the software side of things, specifically working on the visualization and augmentation of Jacquard's gesture catalog. So what you see right here are the 4 existing gestures that Google supports. You have brush in, brush out, cover, and double tap. And with each of these, you see a corresponding visualization of how those gestures look with our toolkit. In these visualizations, time is communicated by the scrolling motion, similar to Dance Dance Revolution or Guitar Hero, if you guys have played. Same idea. And the brighter the color, the more pressure is actually being applied. So that's how you can actually read these visualizations. Now, our team over the last semesters has actually also uncovered a 5th gesture that, while included in Jacquard's firmware, was not actually exposed to users. So that we dubbed as Scratch. And you can see right here, it's this back and forth motion. Here's a corresponding visualization for that. Now, in terms of introducing new gestures, we wanted to leverage a second dimension of user input. Now, we wanted to identify and use pressure actually as a second dimension, and that's where Force Touch comes in. Force touch is a gesture where users are required to apply 2 levels of discernible pressure on the jacket's left cuff in this case, and without raising their hands in between, the gesture actually is then recognized. To accomplish this, we had to do a data pre-processing and model-based approach, where we took 45 subsequent readings from each of the 15 threads and flattened that into a single input vector, and you feed that into a neural network to actually achieve the following results that you see in this GIF. Now, one thing is, you'll see this network actually hasn't converged, and there's also a very heavy bias towards negative samples versus positive samples. What's actually happening here is we're doing a binary classification and identify whether a yes is an example of force touch or no is an example of another gesture or the lack of any gestures. And because of the latter, there's a lot more negative examples than positive examples, and this is something that we'd like to balance out in future iterations. For the time being, to show proof of concept, we've actually been able to implement a warm-up and cool-down post-processing procedure, and that's what yields these results. The aforementioned software and toolkit and the Cocoa Pod is all available at this link, and we'll be providing further links later on in the presentation.
All right. So to determine how we could export this technology to potentially other garments or do-it-yourself projects, the first thing we had to do was take apart the jacket's cuff. So When you flip the cuff over, it exposes a stretchy windbreaker fabric and a black lining on the underside of the denim. Removing that black lining exposes the 15 conductive threads very clearly here. It also exposes a plastisol layer. This is a very thin plastic layer that provides electric insulation and also washability up to 10 times in the lifetime of this jacket. Removing this layer exposes the connections of the 15 conductive threads to a flexible PCB. These can be easily severed and replaced with connections to other 15 conductive threads, so you can apply to other technology as you develop it. There's also the snap connector here, which is a 5-pin I2C connection to the jacket tag. On the flip side of that connector is the capacitive sensing microcontroller. The purpose of this controller is that it translates analog signals coming from each of the 15 conductive threads into a digital bit stream that is then transmitted to the tag using I2C communication. So now we broke down the tag, and these are the highlights of the external outlook of the tag. We have a USB connector used to charge the battery of it. It's got a flexible silicone body allowing it to be bendable in the sleeve of the cuff. And it's got an LED indicator. This is used to give an update on the battery status and also gives gesture confirmation and connectivity confirmation, as well as a vibration motor, which provides haptic feedback when a gesture has been sensed. On the right, you'll see the snap connector at the very bottom, which is actually what plugs into the cuff, and at the top, there's hard plastic, which encases the battery. We took this completely apart, and you'll see in the very center, there's a flexible PCB ribbon, and that's actually what provides the tag its flexibility. And it acts as the bridge between the battery charging unit, which you'll see on the right, there is a charging circuit, which the USB connector charges. And on the left, we actually have the brains of the tag, which is the PCB. So taking a deeper dive into the PCB, we've got a Nordic microcontroller, which is the brains of the tag. There's 6 I2C programming pins on this board, which are normally left out on commercially produced PCBs because they're not typically meant to be hacked. So this tells us that this board has actually been meant to be hacked. We've got 4 LEDs and what appears to be an IMU, which its functionality has not been implemented yet, and so this could uncover a wealth of accelerometer and orientation data for us. On the flip side, we've got the male pogo pins, which plug into the jacket, and power to the vibration motor, and pads for the flex PCB connection.
So we imagined several future applications of e-textiles. You can imagine wristwatches, athletic wear, and we even have talked about doing a backpack strap, which is agnostic of the actual specific article of clothing you're wearing at any given time. And now we have documented all of our work, and you can read more about it in the Medium articles linked here. And we'll also open up the floor for questions. This is our email and contact information if you are interested in reaching out.
Thank you. When you said you get a bit stream, so are you just getting raw binary values, or over the I2C, or is it doing like analog, or what's it giving you?
So we actually haven't been able to examine the bit stream ourselves because of when you plug in extra wires, it causes the tag to go into a weird state because of the extra resistance. But we are assuming that this is the case because typically capacitive sensing controllers work that way. They usually take a reading and convert it to, I think, a 10-bit reading to represent the analog capacitance value.
So when you read the I2C value, are you reading the I2C value?
No, so we haven't been
I see.
able to do that yet because of that
Gotcha.
resistance thing.
Any other questions?
When you were training the neural net for the new gestures, you were saying, so you have the input from the 16 threads and you take that over a certain period of time, or what's...
How does that work?
Yeah.
Yeah, so 15 threads, and basically we take 45 consecutive readings from those threads. And so we combine that into a single vector, and we feed that into our neural network. So essentially you're getting a kind of time window, and that is the input to your actual classification problem.
And at every time step, you're collecting the next 45 and the next 45.
Yeah, it's like a sliding window approach, basically, where you take in the current one and you discard the oldest one. Taking the current, discard the oldest.
Any other questions?